Okay, guys, welcome back to your last part of the Science 10 Physics unit, which is talking about efficiency. So far, we've talked about energy transfer, the development of the steam engine, kinetic, potential energy. Now we're going to merge it all together in one little fun calculation. So let's get started. So when we take a look at the internal combustion engine, let's review what we talked about last time. What energy is being converted in this kind of engine? So internal combustion engine, fuel burns, produces gas, and expands and makes kinetic energy. So in essence, what we're doing here is we are taking chemical energy and we're converting it to kinetic energy. Okay, so again, like we talked about, when we're breaking the bonds in chemical energy, it's turning and converting it into kinetic energy. But what we know in this process is that some energy is always lost as heat energy. Okay, so again, this process going from here to here can never be 100% efficient according to our laws of thermodynamics. Okay, so again, we have to keep these principles in mind as we go forward. So generating electrical energy. Okay, another way we generate electricity is through a generator, a device that produces electrical energy. Okay, it has two parts. Okay, a magnet and a coil of wire. Okay, as in our diagram here, we see a magnet and we see our wire in here. Okay, so what we end up doing with the generator is we have to move the wire coil through the magnetic field produced by the magnets. What this does is it ends up generating a current for us. So what we end up seeing is this bundle of wire ends up rotating. Okay, and again, there's a variety of ways we can get this thing to rotate. When this rotates at a super fast pace, we end up seeing electricity be generated. So when we generate electricity, okay, electrical energy by fossil fuels is about 10%. So when we think of burning fossil fuels to produce our electrical energy, we think of it as about 10% being efficient. Okay, what are the major differences and similarities between the following plants? Thermoelectric generating plant, thermonuclear generating plant, and hydroelectric generating plant. Okay, we have to take a look at what the root words of these are. Thermo, meaning heat, electric, meaning electric. Okay, so again, we end up seeing heat and nuclear. Okay, so again, we're using nuclear energy to produce heat. Okay, we're using heat to produce electricity. Okay, and then again, hydro is H2O, or water as we like to call it, to produce electricity. Okay, so we can take a look at what we see here. In the thermoelectric generating plant, we're burning coal to heat steam. Steam then turns a turbine, which turns a generator and turns that wiring that we talked about in the last diagram. The next one, for example, the thermonuclear generating plant, nuclear fission produces steam. Okay, so again, it uses nuclear fission to produce heat and tons of energy, which produces steam, which turns a turbine. Okay, and then the hydroelectric generating plant uses the kinetic energy from water to turn the turbine. Okay, so we can see a whole bunch of different ways of converting energy, but again, the laws of thermodynamics state that they are not 100% efficient. So electricity from water. Electricity formed from kinetic energy following water that turns a turbine. It is clean and efficient. Okay, however, the downside of this is it creates large lakes or reservoirs. Okay, another downside is we often see fish get caught up in this whole process. Okay, so again, what we end up seeing here is we end up seeing water flow down the chamber, okay, and through the turbine. This turbine spins and rotates, okay, to turn a generator. The generator produces the electricity, and the electricity flows out through the power lines into our wonderful city. Okay, the water then flows out of the reservoir, okay, and continues on its way. This is the whole hydroelectric plant that we just talked about. Okay, a lot of issues with this. Okay, we have to think of how it affects wildlife. Okay, again, we see fish, we see a whole bunch of aquatic life go through the turbine and get hurt. It changes the aquatic environment as well. Okay, so always some factors to take into consideration. Coal-fired thermoelectric generation. Okay, this is the most common in Alberta. Okay, coal is burned to heat water to steam. Okay, steam is forced through pipes and spins a turbine. The turbine spins the generator, producing electricity. Electricity, again, just like before, leaves on the power lines. Okay, and we can see this by looking at our little diagram at the bottom here. Okay, we see the river. Again, it comes in to, it's brought up into the boiler where it's heated up into steam. Steam passes through here and goes and pushes this and rotates the turbine, which rotates the generator, and the generator produces the electrical current, which is then put into a transformer and sent away. Okay, but again, you're using coal, you're burning fossil fuels to heat up steam to do work, to rotate the turbine. Okay, so let's keep moving on. Last but not least is we look at nuclear energy. Same kind of process as what we talked about in this last one. Okay, we see water come in. Okay, we see water come in. We see the contaminant structure where the reactor vessel is taking in, again, releasing nuclear energy that we talked about before, and turning the water into steam. Okay, the steam then travels through the turbine, turns the turbine, okay, turns the turbine, and then we end up seeing the electricity go into the generator, same kind of thing. It turns the generator, produces the electricity, and the electricity goes out through the power lines. The water then is brought back down, condensed, and then continues the process again. Flows up through here, okay, up through here. Okay, it's a big cycle, and it continues to happen. Okay, again, it all is based on how we turn the turbine. Okay, and again, with the thermoelectric as well as the thermonuclear, we are just using and heating water in order to do that, to turn that turbine. Okay, so that is key. So there's other methods of trying to capture this as well. Let me get that out of the way. There's solar energy, captures the energy from the sunlight on solar cells, which converts it to electricity. There's also wind power. Okay, turbines spin due to the kinetic energy of the air, which again, if you think about it, when you have the, in this picture here, the generator would be up there. Okay, so we'd see the generator up there. As the blades spin, it's turning the axle on a generator, and what we end up seeing is electricity be produced and run off somewhere else. Okay, so again, two other options for alternative energy sources. Again, both have different faults of their own. So now we can look at efficiency in the second law of thermodynamics. The second law of thermodynamics states that no process can be 100% efficient. Some energy will always remain in the form of thermal energy. Okay? The energy that performs the intended task is what we call useful energy. Okay? Or the output energy. Okay? The energy converted into a form that is not useful is called wasted energy. Okay? When we think about a light bulb, okay? A light bulb produces useful light energy. Okay, however, there's also wasted heat. So we would say that the useful light is what would be the useful energy or the output energy. Okay? Trapping and converting solar energy. So again, when we take a look at the efficiency of a natural system, we could take a look at plants. Okay? What part of the plant is responsible for trapping and converting solar energy? The chloroplast organelle. This is something we're going to talk about in biology a little bit more. Okay? But specifically the chlorophyll pigments. The efficiency of a plant in this process is roughly about 26%. Okay, when we think of mammals trying to convert energy as well from foods, it's even less efficient. Okay? So cogeneration. What is cogeneration and why is it important? Okay, cogeneration is using wasted thermal energy or thermal heat to heat other buildings or factories. It essentially doubles the efficiency. So it's taking all this wasted heat energy from these different processes and using it positively. It increases the efficiency of the process and kills two birds with one stone. So when we talk about efficiency, we can actually run a calculation as how to put this percentages. We've talked about some percentages already. Okay, efficiency is just useful energy divided by the total input energy times 100%. Okay, most machines involve many energy transformations. So it's key with these calculations to figure out, number one, Okay, what energy are we starting with? What energy are we starting with? Okay, again, if we start about when we take a look at a roller coaster, for example, okay, one of those steep drops that make you want to cry. Okay, up at the top here, we're always starting with potential energy, and at the bottom, we convert that into kinetic energy. Okay, but again, as we move down through the system, and we're going to here, we always lose energy. Okay, we lose energy in terms of heat. Okay, so again, our potential energy will not always equal kinetic energy like we talked about before. Okay, but in the terms of efficiency, our potential energy would be equal to our input. Okay, our kinetic energy, again, a roller coaster is meant to move, so our kinetic energy would be our useful. Okay, and so based on this understanding, we can figure out, based on these two, since we have an input and a useful output, we can figure out the efficiency. And we'll do some examples together. Okay, so Mr. T's van uses 1,215 kilojoules of chemical energy to generate 334 kilojoules of kinetic energy. What is the efficiency of the van? Okay, so we know the efficiency is equal to useful over total times 100. Okay, so again, we know that he uses 1,215 kilojoules of chemical energy, or gasoline. So the gasoline here would be equal to our total energy. Okay, our useful energy is, again, it's a car, so useful energy would be our kinetic energy, which is 334 kilojoules. Okay, so again, all we need to do now is we just need to plug these numbers in. So what we end up getting, okay, is we go 334 kilojoules divided by 1215 kilojoules times 100. Okay, and this ends up coming out to be 27.48%. However, significant digits play a role. We have 3 here, we have 4 down here, and so our answer should have 3. So our answer should be 27.5% efficient. Okay, again, really low. Okay, so that's an example of efficiency. Now, we're going to see some examples that are not so, that won't just give us the energy right away that we want. Okay, so let's take a look at this next example. It's good practice. What is the efficiency of a 1,600 kilogram roller coaster which is released from 110 meters and reaches a speed of 23 meters per second at the bottom of the hill? So let's look at what's important here. We have a mass of 1,600 kilograms. Okay, we have a height of 110 meters. Okay, we have a speed of 23 meters per second. Okay, and we know it's a roller coaster. So let's draw a little diagram just to remind ourselves what's happening here. Okay, so we're starting with potential energy up here. Okay, it's going down here like we drew earlier, and it's ending way down here, and it's going super fast. Okay, again, it has kinetic energy. We know that from before. Okay, so what we need to do is we know, again, with the roller coaster, the input energy here is our potential energy. Our output, or useful energy, is our kinetic energy of this course. And again, given our variables, we can use the mass and the height to find potential energy. Okay? We can use the we can use the mass and our velocity to find the kinetic energy. Okay? So we need to take this one step at a time. So let's move that up. Okay, let's find our potential energy. Okay, potential energy, as we know from before, is m GH. Okay, so again, we have 1,600 kilograms times our 9.81 meters per second squared times our height of 110 meters. To give us an answer of 1,700,026,560 joules. Okay, our kinetic energy. Kinetic energy is equal to 1/2 mv squared, like we talked about before. Okay, so we go 1/2 times 1,600 kilograms times 23 meters per second, all squared. Okay, again, we do the square first in our calculator, and then we plug everything else in to give us an answer of 423,200 joules. Okay, so again, we have our output and we have our input. Okay, now we're going to take these and plug it into our efficiency equation. So we do the total input over useful output times 100. Okay, so now we just plug in our numbers and solve. We know our useful output was 423,200 joules. Okay, we know we have two significant digits here from our calculation, and our input was 1,726,560 joules. Okay, and again, three significant digits from the calculation. And we end up getting an answer. We times that by 100, and we get an answer of 24.5%. Since we have two significant digits, it becomes 25% efficient. Okay, so again, we won't necessarily always be given the easiest questions to do. Okay, so they won't always just be given you the answer. You have to apply your mechanical energy understanding, your kinetic energy, and potential energy understanding to figure these problems out. Okay? So I want you to take a few seconds, write down 4 or 5 key understandings, and bring them into class tomorrow. I'm going to be expecting you to practice these calculations tomorrow. So if you don't understand something in this that we covered in this video, go back, rewind, take a look at the calculation, and bring your questions to class tomorrow. If you, again, thank you for listening, and I'll see you in class tomorrow. Good work.